activity project, which is part of the exascale computing project of the US Department of Energy. The series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley, and will be the host for today's webinar, Software Packaging. The webinar will be presented by David Rogers. David is a computational scientist in the National Center for Computational Science Division at the Oak Ridge National Lab, where he works on mathematical and computational theory jointly for multi-scale modeling using high-performance computing. He obtained his PhD in physical chemistry from University of Cincinnati, followed by a postdoc at Sandia National Labs and a faculty position in the Department of Chemistry at the University of South Florida. He joined Oak Ridge in 2020. He has published on a range of topics, including statistical mechanical methods in liquids, biomolecules, and quantum models, small non-equilibrium systems, hydration, and finite size effects in nanoscale devices. We have issued around 200 tickets for today's webinar, and all attendees have been muted upon entry. We'll be receiving questions through the Zoom chat and also the Google Doc. We'll be pasting the URL to that doc in the chat momentarily. We have asked David to add breaks during his presentation so he can respond to the questions that come in. David, I'll stop my sharing and you take over, please.
All right, my slide should be showing.
Yep.
Hi, everyone. I'm David Rogers, a computational scientist, as Osni introduced. I guess I should also say David M. Rogers, not David H. Rogers. There's another David Rogers who is the author of the cinema package for visualization. I'm David M. Rogers. So my specialty and background is computational chemistry. Having done that, I appreciate a whole lot packages that I work with that are structured as libraries. And every time I'm building scientific software, I'm always trying to think about how can I make this software easier to install and to use? And how do I depend on other packages reliably that are the packages that I'm going to need to import in order to get my work done for today? So this presentation is kind of my collection of ideas about that. This slide just shows the preferred license and acknowledgement for this presentation I'm giving today. I want to put my acknowledgements up front to thank all the developers that I work with, a lot of these on a daily basis, especially the IDEAS team who helped give me some feedback on early versions of this presentation. I also work with several development teams that are listed here, and some of them are kind of featured as examples. Let's see, and I'm on the Coral 2 packaging work group as kind of like a super minor role in just trying out some of the, listening to some of the packaging progress that's happening there. So there's a lot of fantastic stuff that's happening in packaging and supercomputing. For the talk today, I am going to go over maybe just some general guidelines that are why package and what are we trying to accomplish? What's the definition of done for a software package and release process? Then I'll go through walkthroughs that are the technologies and kind of the conventions that have worked really well to put together software packages with minimal effort that are usable, also with minimal effort. I'll talk a little bit about containers just briefly because it's involved in this whole packaging space. And then because I really like to go to real world examples to illustrate what I'm talking about, I've picked out a couple of good ones from the wild that are trying to accomplish performance portability and package their software in a reproducible, rebuildable way. So first off, before we even get started with packaging, why package? We're all familiar with that undocumented feature or the undocumented code that looks really great on the surface or from the literature where they say that they've done all these great things with their software, and yet when you pick it up, there's really a lot of question marks as to how you're supposed to install and get working and use this thing. So here is kind of the simple cartoon of a person who just pushes the button, but then ends up running away screaming because they weren't really sure what was supposed to happen after they pushed the button. As you're packaging, the key questions that you actually want to make sure that you answer are, what does this package do? How do I set it up as a user? And also explain really well any kind of automation that you've put into your package, because automation can be great, but it requires great documentation. Another concept that I want to emphasize as I go through this talk is that as you're packaging, you should think about the packaging process both from the producer of software, so the developer mindset, where you want to be able to click the build and test button and get to a state where you know your software is releasable. But you also want to think about packaging your software from a downstream perspective, and a downstream are the consumers of your package, the people who will be importing your package as they build their own software. And so those downstreams, you can say they're downstream developers or users of your package. They also have a perspective which is important to think about as you're going through the packaging process. All right. Also on kind of to finish up the idea on why package, standards and conventions can save everyone time. They make life easier because if you package in a standard way, it really removes a lot of guesswork from your user's perspective. All right, so let's jump into general guidelines and themes. If you start from a portable build system that has a great make or CMake or configure install process, that portable build system is what you can base your packaging strategy off of. So I'm not just going to talk about the portable build system, although it's a big part of it, but I'm going to say that creating a portable build system is kind of like your base to start exploring on different systems and using your code in different ways with different downstreams, etc. As a general idea, it's great to always keep your source and documentation together so that every time you make a change in your source code, you can make a change in your documentation. LAMMPS, as the molecular dynamics package from Sandia, does a really great job of keeping the source and the documentation synced, and you can see, when people update the source, they usually go and they also update the documentation. IDEAS-ECP, which is another example, I'll show some of the build process from here because they do great on their build process. They created a separate repository to hold their documentation. So your mileage may vary. Sometimes your own circumstances say we have to separate source and documentation. I would generally recommend keeping them together. In the same vein, you want to keep your source and tests together. So where your software package sits, and you have your source and your headers, you should also have tests there, so that as you change your source, you can also change the tests, and it keeps everything tested easier to keep in a tested and working state. Some repositories and projects maintain separate reference artifact repositories, though, as kind of a note. And I think that's also a good practice because in HPC, a lot of the ways that we test our software is to run the software and compare the output to a reference artifact. Keeping those reference artifacts in a separate repository just keeps all the data separate, and your test process can download the reference artifact and check if that's okay. So keep the source for your tests with your source, but keep maybe the reference artifacts separate is okay. As you start to build your software, and get larger and larger, get a larger code base with more functionality, you always want to be thinking about making modular codes. And so as you build more functionality, you should always be asking the question, can I take a piece of my source code and write it as its own separate package? And this is especially true for optional components or abstraction layers or glue code. One good example is Blast++, and the Blast++ library, or is it called the Blast PP library, is a wrapper for a whole bunch of different ways to talk to Blast, but it gives you C++ templated matrix multiplies so that you can talk to it from a C++ code, but underneath it's calling basic Blast. So those kinds of abstractions can be really helpful to package up and make as their own separate software package. So finally, on guidelines and themes, I want to talk about some do's and don'ts. Thinking both as a developer and as a user, it's good as a developer to have your continuous integration, or CI is continuous integration, where you're building your source code and you're testing it as you're putting it up to the public GitHub repository. It's good to have a CI level integration test that simulates an external user downloading and installing your package and its dependencies for the first time. So that high level test is great because it shows the user perspective every time. As a developer, we can forget that because we have a lot of the dependencies sitting on our system already and we don't think about them. But users may see a new version of the dependency and you won't know about it until you get a bug report saying, oh, we now have to go back and rethink our software stack. So this is a way to avoid that. You do want to document a manual install process that would be what steps you would actually run if you did this manually. So not just like the artifact that's in the CI that explains, to a computer how to install it, but also document the process for installing. A lot of projects go one step further and actually give you some helpful hints on installing dependencies. Some examples that I can call out are Pick on GPU's documentation tells you how to install Boost, which is great because Boost can be complicated to install, but if you go and look at their documentation, they tell you how to install it, and now Pick on GPU becomes a lot easier to install and use. Similarly, for DFT-FE, they have a giant dependency on DL2, which is a finite element package, and DL2 is complex to install, but DFT-FE documents how to install it specifically for use in this package. You can actually look through the GitHub Workflows folders as a last resort for packages that don't do this, but I recommend talking about your install process. Don't assume that everyone has access to apt-get or some sort of virtual machine for getting all the dependencies and running them. Talk about how you would install them through the shell so that your users can, so that users on systems that just have shell access as a user can think through how they can get all their dependencies up and running. As a consumer, on the other side, there's advantages to the developer because as a consumer, once all the documentation is sitting there and your package is tested and it's supposed to be working in an automated, semi-automated install fashion, you have the ability as a downstream, as a package consumer, to go and talk to the development team about the install process. You can complain politely if something doesn't run as documented, and you can actually contribute back vital fixes just in the form of how do I compile this package. It's also good if you notice that there's an issue with documentations for your upstreams to go and submit issues and talk to those developers, because that way the developers know you're there and you're using their package. But also they get contributions so that the package is easier to use. Okay, so I'm going to move forward to simple walkthroughs unless there are questions at this point. I can't see the questions if there are questions. Okay, so we'll move on. Some simple walkthroughs that just show some pretty well tested conventions for packaging are, I'm going to give you a Pi scaffold example, some CMake examples, and a little bit of a SPAC example, so that you can see that just high-level pictures of some conventions. You've probably seen these as well, so I'll talk through. They just kind of point you to the main ideas. Before you start to package, there's a couple of things you should think about and think about with your developer team, which would be, is this package something I'm going to reuse? Could I see myself as a user of this package downloading, installing, and depending on it? Is the documentation good enough that another developer can quickly get it working? Because if your documentation isn't good, you're going to have to start here. And so you have to be ready to work on the documentation and get that going as your packaging proceeds. It's also, if you're part of a large developer team or part of a big project, you have to think for a minute on whether or not you can hold development of new features while you package up what's here. If your project is large, it can be non-trivial to actually hit the pause button and say, this is the set of features we want to create as release number 1.0. It's also important to ask if you've tested this in practice. So do you have enough tests that will start from a clean copy, follow the directions, and run a few tests and show that everything is green and ready to go? As you package and release it, you will also be able to interact with users. So what kind of support do you want to offer, or do you want to put in a disclaimer as to how you're going to interact with users? You should also consider whether you've put in a license, what license is required. At some, at the DOE sites, there are probably there's a process that you should go through, that you should be able to talk to your site contacts on getting a copyright assertion and what kind of review process your source code needs to go through before you can publish it. And also, finally, as you package and release these things, you're going to have to use Git branches to somehow show what state your project was in when you released it. So you should have an understanding and a documented understanding of what branch names you're going to use for your releases and what your tags are going to represent. And of course, capturing those in documentation is great so that people who look at those numbers and names can know what they mean, but also for other developers on your project. So here's a simple example that I'll be using just to show the basics of packaging. Go ahead.
Hey, David, I have a question for you here. I think it's a good point. So what do you mean by packaging in this context here? Does it mean everything you need is packaged together to the point of almost plug and play?
There's different kind of, yeah, so the definition of done, right? So I would say your package is done and released if you say, if you have a document that describes how someone will use your software. Your document could be as simple as copy this Python file to your site packages folder and import it. Or your documentation could be a little bit more complex and say what dependencies it's going to use and give you examples of different ways to use your software. But for the purpose of this talk, a package is a documented process for using your software.
Okay. Go ahead, please.
In the example that I'm developing, I'm going to show, the common, the big three types of software that people release. They're Python, C, and Fortran executables and libraries. And for those, there's some tools that I can talk through that will get your package to a state where the documentation doesn't have to be 15 pages long on an explanation of how to use this thing. If you use the Python packaging process I'll talk about, or the CMake package process, then your documentation can be as simple as CMake install, and then for importing, I'll show you what the import line looks like. So the example is super minimal because that lets us start from something that we can build on. First question to ask is, how will other projects use this work, right? I've got a heat equation solver that's going to do the time integration of heat along a one-dimensional line. Other programs will see, other downstream users will see this as executables that work with the artifacts that the code generates, right? So if I've got an array of heat as a function of one dimension, then I'm going to have some tools that I release to deal with those. I might also have different serial and parallel run programs. Those would all go into prefix bin. Headers usually go into prefix include project. So if other programs are going to use this as a library, they'll have to include the headers, and then they'll have to source the libraries as they compile. So these would be the install locations for headers and libraries. And mostly I'm going to talk about headers and libraries because executables are relatively simpler. Okay, so the front lines of this, of course, are documentation. I should explain what each one of these things does to my users so that they know, okay, if I want to use this program, I include heat.h and I link with libheat.so, and now I can use all this cool functionality. The functionality is explained. As a general, as I go through each one of these different programming language conventions, I'm going to use this kind of workflow. First, document what the end users are expected to do, then kind of structure what targets and by target I mean the libraries and the executables, what targets I'm going to install into the system. Then test the install run process. If it's working, of course, then we can do the tag release and create downstream dependencies and work with users, etc. If it's not working, then we go back to the documentation stage. From a user's perspective, and this should be like a nice review slide, importing a Python package can work in a basic way or an advanced way. And the basic way is just to basically, as I'm building my own multiphysics program, I say I require heat equation at a certain version greater than 0.1. Then I can use pip to install this requirement for my heat EQ. Then my own program, I set this to the Python path, which contains the place where these files were copied. And my app imports HeatEQ. In an advanced usage, I can actually use a package manager to install HeatEQ. And in that case, the user would actually be able to create a virtual environment in Python, activate the virtual environment, and install my package into their virtual environment with pip. So I'll show you kind of the advanced case. This one is more of a copy paste case. This one is using a tool to help you install your package. Setup.config is the file I'll talk about in a second. And also, let's see, you can import from HeatEQ different parts of HeatEQ that are inside of HeatEQ's list of libraries that it creates. So in the Python library structure that I've talked about, let's say my Python heat.py file includes a params class, an energy class, and a simulate function. Those will eventually get copied to a HeatEQ subdirectory. In order to use this thing as a Python package and in modern Python conventions, I have to have an init.py sitting inside of HeatEQ, even if it's empty, so that when I'm importing names from inside of HeatEQ, I can ask for heateq.pheat, so I'm getting stuff from the Python heat file. From inside of my own package, I would use .pheat import params to import the params class. So say that there's a file next to pheat, it would use this kind of import statement. From a user's or downstream perspective, if I'm importing something from this file, I would use from HeatEQ, like the name of the package, the name of the file, import simulate. And you can customize this from here, but this is kind of the basic idea. PyScaffold will give you a nice way to a canonical install method for your Python package. What PyScaffold does is you can pip install it and also pip install the tox tool so that you can use a lot of the functionality of PyScaffold. What it does is it creates the basic scaffolding, the files like setup.py and setup.config that Python understands and knows how to work with, so that you don't have to memorize the exact format of all of the Python setup files. You take this basic scaffold and you customize it for your own use cases. And I'm not going to go through all of that. I'm just going to give you kind of the before and after picture, because I'm sure that you guys can customize this yourself. I want to mention that it has great presets for writing tests, doing documentation with Sphinx as part of the build process, and even publishing your package to the PyPy package index. So I actually was able to publish a Python package called MPI list this way. All right, so after applying PyScaffold, basically what it's done is it's pasted a lot of boilerplate in here that you can now go and customize. Setup.config is one that you definitely want to customize, because you can tell it a list of projects that your project will depend on. So if I wanted to use some sort of advanced numerical solver that can be imported through Python, then I would list it in setup.config. Also notice that it imposes kind of its own directory structure. It wants you to put the name of your package inside the source directory. And now inside your README, you should also be careful to follow through with what I'm telling you to do here is explain to your downstream users how to install your package. So you should put a note as this package can be installed with pip-e install. The -e is, you can check the manual on this button, but it makes it editable. So as a developer, you can edit and iterate. All right. So having talked about the Python example, and if you go online and look through the slides of this, you'll get the links and be able to get more details on each one of these examples. I'm going to move on to the C++ package example. In a C++ package, there's a basic install. It's kind of a basic use method that a user would see, and an advanced use method. The basic use method, users will just manually be telling the compiler where to look for the installs in the libraries. RPath is great to use so that your executable knows where the library is after the link time. So at runtime, it can actually go and check this path to find the library that it was built with. Inside the C file, of course, your number including the header file, and you can just use the names that are now in the library. In the CMake method of doing things, you don't write the arguments to the compiler directly. Instead, you create a target, which is the application target. See, I don't actually have the line in here that creates the target, but we create the app target and we tell it that we need the app.cpp file as the source for building the app target. To link it to the library is the key part, and in the CMake way of doing things, HeatEQ is a package which CMake can find the package definition for. And once CMake has found its package definition, then you can say that my app program is going to link on the heat target provided by the HeatEQ package. And now I'm able to do things like use the CMake generation facilities to generate an input config header that turns CMake define into number define, enable heat equation as 1. The way that the programs, the way that the source files themselves get built is pretty standard. G++ with shared will create the heat.so shared library, and the headers basically get copied into include. It's good to put your package name here so that you don't pollute the main level include directory. And then I would include heat.hpp or include heateq/heat.hpp, depending on how you want to document and use your program. Something to watch out for as you start to build complicated software libraries is that if I'm building multiphysics code that's depending on multiple things and also depends on this heat equation, but heat equation is depending on other upstream libraries, so upstream to downstream, then I start to have transitive build link requirements, things like compiler features that are needed to understand headers, or linking features. All of these kind of trickle down so that the multiphysics code has to be aware of a lot of nuances and compiler flags that it needs to run with in order to get all of this stuff working at once. There are ways to solve this problem. Package config is one of them. That's the kind of the automake method. CMake is another one where, as I just explained, CMake can install a project config.cmake, which defines a target. Here's what goes into those targets. I think it's a little bit verbose, but it's workable, and there are examples out there that you can start customizing. I'm linking you to a couple of examples here for just kind of a very basic, here's how you create a CMake target that releases a library. What a CMake target is it's a list of source files that create a library or source files that create an executable, but also you can give that executable or library attributes like I need the C++ 14 standard. And those attributes, CMake knows how to turn into compile flags. So as you build your program, you create a bunch of targets. You can install all of these targets as a package file that CMake can import later, so that your downstream users don't actually have to redefine what your targets and flags were. They can import this package, and as they import the package, they'll know about all your targets, and so they'll know about all of the compiler flags they need to run. Another piece to this that I'm not going to have too much time to talk about is a config CMake in, but this is essentially like a little piece of CMake code that your downstream users run just to double check that they can use your package. Okay, so I've gone through the CMake lists, probably the most complicated part of this talk, and I've not given it all the detail that it needs because there's a whole lot of great documentation and resources and examples out there. This is kind of the view from 1,000 feet. Once you've gotten your CMake working and you're happy with your CMake install process, check and run your tests with CMake. If you've put in C tests, then you can run C test. make sure that you go through kind of the manual steps that you do are to go through and update your changelog. Again, work on the documentation. Create a tag when you're happy with everything and the documentation is good that says what you did, and creating your tagged version so that users can see these tags. When you publish these things to GitHub, then it will look like a list of tags that have been published to GitHub. And you can see each one of these tags as kind of a tagged release of your software product. This is what it looks like from the downstream. In C++, there's not as great of a find the newest, latest, greatest version feature as there is in Python. So in C++, you're really kind of throwing your software over the wall and saying, here's a tag, everyone needs to go find it. You can actually help users to find those by mailing lists or ways that you contact your users, talk about the new changed features, et cetera, and why people would want to switch, what's changed. You have to remember to go back and change your public facing websites and all the pointers and documentation that point to your code. If you've put in a spec package that downloads and installs your code, you have to remember to go change that as well. You might want to create a checklist for yourself on these things. Net result of the CMake process is that we've taken kind of a basic CMake list that worked for us during development, and we've documented it. We've added config CMake so that CMake can install its list of targets as a package. And I've also included some tests here so that CMake could run them as part of its testing process. All right, so I want to stop and ask for questions before I move on. I don't have time to go into all the details of these things, but I'm hoping that I can kind of explain the process and what developers are doing as they're going through and making their source code ready for release.
David, there is one question here. It appears that exascale researchers are moving towards CMake. What is the main reason?
There are a lot of competitors to CMake and other kind of standard, how do I want to say this? There's a lot of conventions and standards and package manager utilities that are out there. But I think the DOE tends to be rather conservative and check things that are going to have enough support and work on the systems that they care about. And so CMake has a lot of examples and documentation and software that are working on some of the on the supercomputers that are sitting at DOE sites and HPC clusters that people are using a lot. And because of the mass of developers who are using CMake, it's a lot easier to build and use it. There are some other tools out there, and you can go and try them, especially if you have good examples and documentation that are close to what you're doing. AutoMake is also kind of what was the standard before CMake. I would say the main advantage of CMake over AutoMake is that it has a different process for creating targets that have attributes, have properties, and your target properties turning into compile flags is kind of its killer feature. Okay, so I'm going to move on. I say a little bit about Fortran library structure in the vein of the C++ library structure. Was that it?
No, go ahead.
Great. So Fortran library structure, I don't have to say too much here because it actually follows pretty much the C++ CMake example. You can package up a Fortran library using CMake. Some of the differences to note here are that with Fortran, you have a single Fortran source file, which when you run gfortran, will spit out both the library shared object and mod files. And these mod files are the equivalent of the headers. And they're imported from other packages by the use statement. So if you install your mod files into something that is namespaced neatly like this, and then you put your library into lib, then this is kind of the convention that people are expecting for being able to cleanly depend on your Fortran package. This line looks a lot like this corresponding line for C++. And I'm not going to show the CMake code again, but it's the same. If I created a CMake module for this, then the CMake module would use the import package command to get your HEDQ Fortran module. I also want to note here that a lot of Fortran programmers like the Fortran package manager because they say it's just a little bit better than CMake. So if you're in Fortran land, you might give this one a shot and see if it does what you want it to do while you consider using CMake. I'm going to point you at some really good examples that I found. For example, this Fortran library, which is well documented. It talks about how to install the library, how to run the tests, etc. And it even has source code that is scanned to generate the documentation. So my key takeaway is to start from really good examples and structure your package following that good example. Last but not least, in terms of conventions that are really helpful for packaging is SPAC. I think of SPAC as kind of a way to document what flags you pass to CMake. In the CMake context, it works that way. SPAC also works with other build processes that are not CMake, but I'm going to focus on CMake here and say that if you create a SPAC package, basically you're creating a package.py file, which has the name of your package as a class. This would replace your build.sh file that manually calls CMake with some -d CMake CXX compiler name equals, because SPAC will provide its own compiler wrappers as it runs this build process to compile your package with CMake. So SPAC can read this, call CMake, and install your program. What this does is it allows you to systematically name packages and their options. So rather than giving a bunch of -d flags that say what options your package was compiled with, SPAC has done all the parsing for you so that you can actually say SPAC install HEDQ, and you can give it other options of a spec which uniquely specify how your package is being built and what it's depending on. So to talk a little bit more about what a package spec is, here's an example from the current way that our system administrators are building software on Frontier. If we're building the MREX package, we pick out this specific version that we've tested and we know is working. We add the plus Rockham, what is this option to the package, which creates the proper -d flag that goes to CMake. And we can disable the CUDA option and set the AMD GPU target. Similar things happen for other packages. The syntax of a package spec is here. And a killer feature of the package spec, again, is that I can use this one-liner to explain the constraints that I want, the version that I want, and even the compiler and even specific dependencies that I want to choose. So if there are multiple ways to provide MPI, this package could say with this dependency spec that I want MPI built in a certain way. And when all this gets compiled and installed, it doesn't actually install into user local. It installs into its own directory. So for example, Hyper-E might install into Hyper-E 2240 this SHA sum, which is telling SPAC exactly the variant of the package that was installed. That means I can install multiple different variants of Hyper-E with different options side by side. There are more things you can add to your packaging process once you've got your basic build and install process down. I'm going to list them here and note that starting from something simple makes it easier to build on and do more with your packaging. You can add things like these extra features, code coverages, type checking, testing tools. Having a good base makes building up your package easier. So again, start from a good build system. Here are a couple other alternatives to CMake. For the reason that I mentioned earlier, CMake is a pretty good path to go because there are a lot of examples and documentation out there. There are alternatives, so depending on what you find, you may want to go with an alternative. Once you have a good build system, now you can start exploring that on different systems and talking to your users about how you would integrate this with the systems. So there are some package managers out there. SPAC you can think of as like a package manager for HPC, because you can say, I want to build my package in a certain way and make sure that all your dependencies have ways to be installed that are coded inside of SPAC. There are some other ways that you can do package management as well. Next, I'm going to talk a little bit about containers and what they can do for package management, specifically how they make it easy to install dependencies and get up and running when you're trying to test your software or when you're trying to get builds that are reproducible and working. There are many container-like abstractions out there. So this slide is a little bit complicated. I just want to focus on the app container right here, because usually when people talk about containers, they're referring to this one, the programs that are running inside of an emulated file system. So that's distinct from virtual machines or guest operating systems. Virtual machines or guest operating systems inside of a hypervisor. Containers are very lightweight because they don't actually have their own concept of an OS. They share the same kernel as your base operating system, but they have an emulated file system so that they're overlaying files that only they see. And that way you can use libraries that look like system libraries, but are actually provided by your own programs. And of course, they run one or two user programs. Usually it's just the entire container is built to support just one program. I'm not going to talk too much about this slide in the interest of time, but it should be in the slides that are published online. Basically, containers let us run apt-get, pip, SPAC, etc. to install dependencies that our software needs. It's okay to actually run the package managers that happen at this level inside of your container, because they're actually making all of their changes to a temporary kind of throwaway file system that sits inside the container. And that way you can apt-get your dependencies or SPAC install your dependencies, then install your own program and then run your tests and then report out. And you're able to and then clear out all of the mess and redo this process. It lets you do the integration level test that I was talking about at the beginning. Basically, the process as you're building your container, or the thought process that you want to go through, is to start from some sort of base image, which it can be a plain vanilla Ubuntu base image, or a lot of people are looking at stripped down smaller Linuxes, and then they just apt install everything that they need on top of that. You can also take one of those and make a new base image by installing some packages and now release your own base image. So there are a lot of base images out there. I would recommend starting from something as simple as possible for your base image. There are a couple of base images available as part of the E4S package, the E4S website release that you could check out as well. The reason you want to start from a simple base image is just so that you have kind of a lowest common denominator that most users will have. Install packages that you need as dependencies, copy the sources for your own program, and then run your program's build and test process. Okay, so just to give you a flavor of what those container build recipes look like, I'm giving you some Singularity image format build recipes that I guess Singularity wants you to call def files. So here Bootstrap is looking for, okay, so this is what the user would see as user documentation. I guess maybe going through the same process that I had before, where we want to document what the user sees and then document what we do. The user would see that we've built our own base image that is heataq.sif, and then they could take this and install their app as copying a file, and then maybe install other things that they need to run their application, and then run the app as part of their run script. In order for the user to be able to use your image format this way, then you could, for example, build an image like this that says start from a very basic Docker image that's Python 3.9. The Python 3.9 Docker image is like a base Ubuntu image, but also includes Python so that you don't have to spend time apt installing Python. Now I copy over my heataq files and I run my own build process. and I can provide some help. So this is the build file for my HEDQ library, which then would provide the CIF image file that your users could use if they wanted to build on top of your image, kind of following this arrow here. All right, and here's the build command that you can find on the Singularity website. I also want to mention Singularity and Aptainer, I guess, are the same project or split off projects. They're closely related projects. After containerization, not a whole lot has actually changed in the package. What we've done is we've just provided this build recipe to explain to Singularity how it could build a container that uses this package. And then I also am thinking it would be a good idea to include the shell script that runs Singularity to make the CIF file out of the def file. All right, are there questions on containerization before I move on?
David, no, I think we can, there are a couple of questions here, but I think we can wait a little.
Okay, I'm aware of the time. I guess I have 13 minutes left, so I want to make sure that I'm able to talk a little bit about these examples, but then also have time for questions. Performance portability is one of those hot topics of how do we get one source code to run on multiple machines and actually have good performance there. And what I'm listing in kind of the fun cartoon are just some doorways that people have tried and that are out there and that you can use. They're OpenMP, which is kind of the techie way to do it. There's a C++ way that has parallel fors, and there's a lot of toolkits that allow you to use these these modern C++ methods. There are also kind of simple simple header file macro, not header file macros, but there are simple translation layers. So we can actually kind of put a band-aid over the cumallocs and still use the cumallocs, but think about them as, you know, this generic malloc that's going to go to different places based on what I do. And then there's the really complicated way that I don't recommend of putting ifdefs everywhere to test what system you're on and using different pieces of code. Try if you can to use the same piece of code, but then be clever about what kind of performance portability strategy you're using so that it's able to compile to the right thing for the right architecture. So I'm picking out some examples of build processes for packages that are trying to achieve the complicated goals of performance portability. The first one I'll talk about is DCA++, which is dynamic cluster approximation that does correlated electron structure. It's a C++ code that does a lot of matrix multiplies, so it depends on the Magma code for its BLOS, but it also has its own matrix math library for some of its special operators. They want to go from CUDA and also add a HIP backend, but make minimal changes. So the solution, of course, is going to be something that's reusing as much of the CUDA code as they possibly can. To do that, what they've actually done is included this CUDA to HIP library, which comes from T. White Cray Quip. And this CUDA to HIP header translation library will basically take every time a CUDA malloc is called and turn it into a HIP malloc just by number defining CUDA malloc equals HIP malloc. They do have a little bit of extra stuff that they do that's slightly different, like error handling between CUDA and HIP. And I've included some references here that you can go through and peruse if you want to take this strategy. Because interoperation of Python with C is also a really common goal for a lot of our HPC packages. We want to compile a fast C code that's going to work at machine speed and then have a Python library that's sitting on top of it. PySCF is a code that provides an extension template. So the problem they're trying to solve is to allow users of the PySCF Python code to make their own efficient C plugins. To plug in a C code into their PySCF, upstream library code, what they do is they provide you a template. They say, here's a setup.py file, and here's how we want you to structure your plugin so that we can compile your plugin and import it and use it use it as part of the PySCF. The actual magic kind of critical part of that template that makes things happen is that they have translated kind of a high-level description of your package that the developer provides So the developer gives a name for their extension module, a list of source codes, and the libraries that it depends on into setup.py. And so the developer, changes a few things with setup.py, but then setup.py actually translates that into stuff that Python needs in order to compile and use that as an extension. So they've provided kind of this little shim layer that lets the user, that lets the developer of the extension document how their extension is structured in a way that PySCF can then import without forcing the developer to look through the import method. Another real-world example is ZFP, which is a scientific data compression library, and it focuses on multidimensional arrays. They wrote their compression library in C++, but they wanted to allow users in other languages to also use that code. So they actually, for Python interoperability, adopted the scikit build process. Linking you here to scikit build. It's really well documented, and it's a great way to build a Python extension module and import it from C++. That also has a CMake process attached to it. The kind of the central piece that makes this thing work is that their CMake lists has an add Python target provided again by scikit build. This Python target makes a extension module called ZFP from a piece of source code that's written in Python. The Python source code is pretty much C. It's like a domain-specific language for writing the extension module that lets you write something that looks very much like Python, but is calling C functions. And so here, the Python function compress array can now call some C functions and use C data structures that are defined inside of the Python-like header files. I'm going to point you to this example, and if you're interested, I encourage you to read more about it. Finally, I want to talk about Cabana, which is a package that does molecular dynamics, depending on some really big libraries. Well, I guess some really powerful libraries, not necessarily big, but Cocos is a performance portability abstraction layer, and it's built using SPAC. And so the challenge that they want to overcome is to actually just explain to users how they can compile Cabana using SPAC and based on the Cocos backend and all the different hardware methods that Cocos provides. The solution is to carefully document the SPAC options that are required from its Cocos dependency. So the key pieces that make this work are the SPAC package for Cabana imports the SPAC package for Cocos. And when it does that, it can ask the SPAC package for Cocos about the backends that it is supporting and about the versions that it's supporting. And then it can kind of copy those transitively into its own dependencies. So it can say that the Cabana package is going to depend on HIP if the Cocos package was built to depend on HIP. And again, I'm giving you the view from 1,000 miles here, and you can dig into these examples and customize them. Also, as a general rule, SPAC is kind of complex, but if you find an existing package inside of it that does a lot of the same processes that you need for your package, then you can base your package on it and get really far. As a conclusion, always document what you're doing. Think about users as you're documenting, and don't think that your makefile or your script is a substitute for those explanations. There are a lot of good standards to choose from, so you want to pick the one that's easiest to adapt to your use case. And as you package, you can use that as a tool to help you interact with your users, improve your own developer experience, but also deploy faster and test your software. So that's all.
David, thank you. I have some questions for you. So one of the participants would like to know your opinion or suggestions on single sourcing a package's version from the source code manager like Git.
On single sourcing, maybe I should switch over and look at the
chat or
the chat itself.
It's Diego Menendez question.
Hi, David. Can you hear to me?
Yes.
So by single sourcing, I mean, instead of writing the version in more than one place, just grabbing the source the version number from the source control system. I know that there's a setup tools package and a setup tools SCM that is able to do that. I wonder if you have any experience with that one.
Yes, and actually, I think PyScaffold sets up your project where you have to put your version number of your Python package both in setup.cfg and inside of your init.py. But there's another example using the Python poetry package manager that populates your program with an init.py that uses setup tools and looks at whatever setup.cfg has defined as your version. So actually, I've worked with both, and I can point you to examples. I'm not sure if I could recall where they're sitting off the top of my head. It's great if you can to reduce the number of places your version number sits in your code. I've also seen in C programs where the developers provide a package and install script which looks at the current Git environment and uses Git to figure out what version it's on.
Yeah, thank you. It used to be done with Subversion very easily, just including a variable name or a Subversion kind of comment in any type of code. But with Git, I haven't found a way to do it until recently, where I found this setup tools SCM, and it seems that it will do the trick. Only it's a bit more complicated, but I'm working through it right now. Thank you so much.
David, another question. I don't know if you're looking at the chat. Is Spec a good way for a user to install a package with complex dependencies if the platform they're using is not already running Spec? In other words, is it feasible or a good idea to recommend users to install Spec as the easiest way to install your package?
It might be. I would recommend just using the recipe git clone spac and source the spac environment and use spac install dependencies as a test to see whether or not spac already has the dependencies that you care about and whether it will work on your system out of the box. Spac usually works on most systems out of the box, in my experience, with only a little bit of tweaking to Spac's packages.yaml file. And so that's kind of a topic for using Spac. It's you install Spac and you start running Spac install and you see if it does what you want it to do. Most of the time, it pretty much does. And so it's great if you have complex dependencies. Deal 2 can install with Spac, and it makes my life a whole lot easier. But on the other hand, you do have to spend a little bit of time tweaking the packages.yaml to explain to Spac what libraries you already have on your system, and you do not want Spac to recompile because it will recompile everything that it doesn't already know exists.
And David, related to Spac, there's a question here. Is Spac comparable to Conda?
Spac is much better than Conda, and every time that I try and use Conda on systems that I've worked with, it always ends up backfiring on me. And the reason is that thing that I just talked about, packages.yaml. With Spac, you can tell Spac what packages exist on your system and that you don't want Spac to rebuild. With Conda, you're pretty much forced into using the set of dependencies that Conda gives you. And that can be bad because a lot of times those dependencies might not be the optimal ones for your system, but a lot of times you have a better idea of what your dependencies should be than Conda does. Also, Conda is installing binary blobs and Spac is recompiling so it can use the optimized path for your system.
And a final question here, David, changing a little. Does container run slightly slower because of some overhead? Or does a container, right? Run is light?
Yeah, so containers are super lightweight, which actually makes them run pretty much at the same speed as the native system. There's a star on that comment in terms of the fact that containers can use their own libraries. So when you build a container and you install a set of libraries into that container and you use them, those libraries might not be you might not have picked the right ones that are optimized for your system. However, if you pick the same libraries and you install them into your container that you have on your base system, all the numbers that I've seen indicate that people are getting the same speed from containers as from their the same speed from containers as they're getting from bare metal. You can also get faster load times on containers for Python programs, just because Python programs look at a lot of files. And if your container packages all those files, you now have a much faster load time because it's looking in the same place.
I think we have we have gone through all the questions here, David. Thank you very much, David. Thank you for all the participants for joining us today. And I have put in the chat, our next webinar in this series is going to be on the October 12th, Investing in Code Reviews for Better Research Software. And there is a link there for people to sign up. Thank you again, David.
Thanks, everybody.
Thank you all.